Calculating incident energy in a motor control center involves several steps. Firstly, you need to calculate the short circuit current, often abbreviated as I sub SC. The formula for this is I sub SC equals kilovolts base divided by the quantity 1.73 times the sub Pu, and then multiplied by 1000. In this formula, kilovolts base is the equipment's rated voltage, which could be 480 volts or 4160 volts depending on the specific motor control center. C sub Pu represents the per unit impedance expressed as a decimal. For example, 6.28% would be 0.628. Secondly, you'll calculate the power in the arc, denoted as P sub A. The formula is P sub A equals 3 times I sub SC squared, then multiplied by kilovolts base, and finally divided by 1000. I sub SC here is the short circuit current you calculated in the first step, and kilovolts base is the equipment's rated voltage in kilovolts. This calculation gives you the power released in the electric arc during a fault. Thirdly, determine the curable burn distance represented as d sub Cb. The formula is d sub Cb equals 0.1 times the square root of the quantity kilovolts base divided by A sub Sc. Again, kilovolts base is the equipment's rated voltage in kilovolts, and I sub Sc is the short circuit current. This distance helps determine the safe working distance from the arc flash hazard. Fourthly, you'll calculate the incident energy, often denoted as I. Incident energy calculation methods differ based on voltage levels. For voltages up to 600 volts, a simplified formula can be used, I equals P sub A times T, multiplied by the quantity D sub Cb divided by R sub B. Here, P sub A is the power in the arc, T is the arc duration in seconds, D sub Cb is the curable burn distance, and R sub B is the working distance. For voltages above 600 volts, the process becomes more complex. NFPA 70E does not provide a direct formula for incident energy calculations above 600 volts. In such cases, IEE 1584-2018 is recommended. It involves using specialized short circuit analysis software to determine the incident energy at the working distance. This software takes into account various factors such as the system voltage, fault current, and equipment configuration to provide a more accurate estimate. There are a few important considerations to keep in mind when performing these calculations. The short circuit current, I sub Sc, is not necessarily the same as the bolted fault short circuit current. I sub Sc represents the current flowing under specific fault conditions, while the bolted fault current is the maximum possible short circuit current. The bolted fault current assumes a direct short with no impedance, which is the theoretical maximum. Also, if the calculated short circuit current, I sub Sc, is not in the range of 16 to 50 kA, the incident energy calculation using simplified formulas might not be accurate. In such cases, it's crucial to use IE 1584-2018 or consult with a qualified electrical engineer for a more detailed analysis. Let's look at a couple of examples to illustrate these calculations. In example 1, we have a system with a 480 volt rating. Using the formula, I sub Sc equals 480 volts divided by the quantity 1.73 times 0.628, then multiplied by 1000, we get a short circuit current of approximately 47.4 kA. Next, calculating the power in the arc, P sub A equals 3 times 47.4 kA squared multiplied by 480 volts, then divided by 1000, we get approximately 351.3 megawatts. The curable burn distance, D sub Cb, equals 0.1 times the square root of the quantity 480 volts divided by 47.4 kA, giving us approximately 4.5 feet. Finally, the incident energy, I, equals 351.3 megawatts times 0.1 seconds, multiplied by the quantity 4.5 feet divided by 18 inches, which converts the working distance to feet. This yields an incident energy of approximately 7.92 calories per square centimeter. In example 2, we have a system with a 4160 volt rating. Since this voltage is above 600 volts, we would use IEEE 1580 Formulas 2018. As an example, let's assume the software analysis yields an incident energy of 11.3 calories per square centimeter at a working distance of 18 inches. Remember, these are simplified examples. Actual incident energy calculations can be more complex and might require specialized software and expertise. Always consult with qualified electrical engineers for accurate and safe assessments. When performing these calculations, it is important to understand the underlying principles and limitations of each step. The short-circuit current calculation provides a basis for determining the potential fault current in the system. The power in the arc calculation estimates the amount of energy released during an arc flash event, which is crucial for assessing the severity of the hazard. The curable burn distance helps define a safe working distance to minimize the risk of thermal burns. The incident energy calculation ultimately determines the potential heat exposure at a specific working distance, allowing for appropriate personal protective equipment selection. In practical applications, several factors can influence the accuracy of these calculations. Firstly, the accuracy of the input data, such as transformer impedance and voltage levels, is critical. Incorrect data can lead to significant errors in the final results. Secondly, the assumptions made during the calculations, such as the arc duration and working distance, can impact the incident energy estimate. These assumptions should be based on realistic scenarios and industry best practices. Thirdly, the limitations of the calculation methods themselves should be considered. Simplified formulas, like those used for voltages up to 600 volts, may not be accurate for more complex systems or higher voltage levels. In such cases, advanced software tools and engineering expertise are necessary. Furthermore, it is essential to understand the role of protective devices in mitigating arc flash hazards. Circuit breakers, fuses, and other protective devices are designed to quickly interrupt fault currents and minimize the duration of arc flash events. The coordination and settings of these devices can significantly impact the incident energy levels. Therefore, a thorough review of the protective device settings is crucial when performing arc flash studies. Another important aspect to consider is the configuration of the electrical system. The layout of the equipment, the length of conductors, and the presence of grounding systems can all influence the fault current distribution and the resulting incident energy levels. Detailed system modeling is often required to accurately assess the arc flash hazards in complex electrical systems. In addition to calculations, practical measures can be taken to reduce arc flash hazards. Firstly, implementing arc flash rated equipment, such as arc resistant switchgear and motor control centers, can significantly reduce the potential for arc flash events. Secondly, using remote racking and switching devices can allow personnel to operate equipment from a safe distance, minimizing their exposure to arc flash hazards. Thirdly, establishing clear operating procedures and safety protocols can help prevent accidental arc flash events. Regular training and awareness programs are essential to ensure that personnel are aware of the potential hazards and follow safe work practices. Moreover, performing regular maintenance and inspections of electrical equipment can help identify and address potential issues before they lead to arc flash events. Loose connections, damaged insulation, and other defects can increase the risk of faults and arc flashes. A proactive maintenance program can significantly improve the safety and reliability of the electrical system. Furthermore, it is important to stay up to date with the latest industry standards and best practices for arc flash safety. NFPA 70E and IEEE 1584 are regularly updated to reflect advancements in technology and improved understanding of arc flash phenomena. Staying informed about these updates can help ensure that your arc flash safety program is effective and compliant. Finally, it is crucial to document all arc flash assessments and safety measures. Arc flash hazard labels should be affixed to equipment to warn personnel of the potential hazards and provide information about the required personal protective equipment. Arc flash study reports should be maintained to provide a record of the analysis and recommendations. These documents can be valuable for training, audits, and future assessments.